Alright, next we're going to look at imaginary and complex numbers, and it sounds scary, but I promise it's not. So first we look at this, 3x squared plus 3 equals 0. How do we solve it? Well, we subtract 3, so we get 3x squared equals negative 3. We divide by 3 on both sides, and I have to get rid of squared, so I take the square root. So equals negative 1. But we can't take the square root of negative numbers. Until now. A French mathematician, René Descartes, same guy who says, I think, therefore I am, proposed that we define the square root of negative 1 as I, so we can solve equations like the one we just did. However, the concept was invented much earlier by Girolamo Cardano in the 16th century, but it was not widely accepted until the work of Euler, who gave us a lot of our geometry, and Carl Friedrich Gauss, who's my favorite mathematician, and has done some other cool little tricks in number theory. And the geometric significance of complex numbers as points in a plane was first found by Caspar Westphal. So the number I is called an imaginary number. Again, I is the square root of negative 1. Not negative 1, but the square root of negative 1. So what do we do with this? Why do we care? Well, now something like this problem we can do, or at least do something. Square root of negative 6. Well, we can't factor 6 and find any pairs. It's 2 and 3, no pairs. So the only thing I can do is take out the negative. Take out the negative and it becomes I. So you poke out your I. And we get I root 6. Same thing here, but now we can actually simplify square root of 45. So we do our pairs, our factor tree. Notice I'm rewriting that 5 so I don't miss it. So I have a pair of 3's I bring out. I have 5 that I stay inside the radical, and that negative comes out as an I. You just poke out your I. Now 150, same thing. We can factor it into 15 and 10, 3 and 5, 5 and 2. So I have a pair of 5's. I bring out the 5. 3 times 2 is 6, and we leave that in, and I pull out the negative as an I. Negative 4 root square root of 9. Again, we just simplify our radical. We got a pair of 3's, no leftovers, so it's 3. Take out the negative, I, and times the negative 4 that was already there. So negative 4 times 3 is negative 12, and the I just goes along for the ride. Now we already know that I is a square root of negative 1. So let's look at some other things. So I squared is going to be, well, remember I is that squared. Well, what happens when you square a square root? They cancel out. We're left with negative 1. I cubed, we can split it up into I squared times I, which is negative 1 is I squared times I, so it's negative I. I to the 4th is I squared times I squared, because remember we add our exponents, 2 plus 2 is the 4, and each of those is negative 1, so we multiply those, we get 1. Then we go up to I to the 5th. Well, we can take out I to the 4th times I. I to the 5th means 5 i's multiplied together, so I split it up into 4 and 1. Well, I to the 4th is 1 times I is just I. I to the 6th, I'm going to split up I to the 4th and I squared, which is 1 times negative 1, so it's negative 1. I to the 7th is I to the 4th times I to the 3rd. I to the 4th is 1. I to the 3rd is negative I. So when I multiply those, I get negative I. And I to the 8th, well, that's I to the 4th times I to the 4th, which is 1 times 1, which is 1. Now look at our pattern. 1i, negative 1, negative I, 1. 1i, negative 1, negative I, 1. So the pattern just keeps going. So I to the 9th would be back to 1. Oops, not 1, 1i. I squared, or I to the 10th, would be negative 1. I to the 11th would be negative I. I to the 12th would be 1, and it repeats. So we divide by 4 and look for the remainder. And when we're doing, and the remainder will tell us what we want. So if I divide 9 by 4, goes in twice evenly, but with 1 remainder. So we got a remainder of 1 here. 10 divided by 4 is 2 with a remainder of 2. 11 has a remainder of 3, and 12 has no remainder. So when there's a remainder of 1, it's I. When it's a remainder of 2, it's negative 1. When it's a remainder of 3, it's negative I. And when there's no remainder, it's just 1. So we're going to look at that. And we just look at the last 4, or the last 2 digits, to see if it's divisible by 4. So we don't care what all the rest of it is. So I to the 18th, we can divide it by 4s. And there's 4 of those. So 16, and we had 2 left over. Well, that turns into 1, and I squared is negative 1, so this is negative 1. Or just divide 18 by 4, and what's our remainder? 2. Remainder of 2 is a negative 1. I to the 35th, we divide it by 4. It goes in 8 times with a remainder of 3, so it's negative I. I to the 21st, divided by 4, goes in 5 times, remainder of 1, so it's I. 108, we just look at the last 2 digits, 08. 4 goes into 8 twice, no remainder. The answer is just 1. 205, just look at the last 2 digits, 5. 4 goes into 5 once with a remainder of 1. So we have I. 67 divided by 4, it goes in 16 times with a remainder of 3. So that's negative I. I here, there's a 78 divided by 4. We have a remainder of 2, which gives us negative 1. And this big crazy thing, we just look here. 87 divided by 4, it goes in 21 times with a remainder of 3, so it's negative I. That's what we're doing. Don't think about it any more than that. So this is how complex numbers and imaginary numbers come together. So if we want to simplify 5 plus the square root of negative 9, well, the real number is 5. This just stays the same. It's fine the way it is. Square root of 9, or negative 9, we have to factor. We got a pair, so we bring it out. And the way we deal with the negative is we pull it out to be I. Remember, you poke out your I. So we have 5 plus 3i. Just like we had something like 5 plus 3 root 7. I is just a square root, so it's the same thing. But numbers like 5 plus 3i are called complex numbers because they have 2 parts, like compound words, complex sentences, and we always put the real part first. So it's what we try and do with the radicals as well. So if we're adding, we just add like terms. Actually, I shouldn't draw it that way. If we're not multiplying, there's a plus sign in between them. So 2 and 5 is 7. And 3i and positive 4i is positive 7i. That's it. Just add them. Just like radicals, because that's what they are. Here, negative 5 and negative 10 is negative 15. I and 9i give me positive 10i. Now, when we're dealing with negatives, what I suggest is that you distribute the negative. So it's minus 15 minus 4i. And then we can just add them up. So 12 and negative 15 is negative 3. 3i and negative 4i is negative 1i, and we don't need the 1. Same thing here. So we got positive 8 minus 7i So 1 plus 8 is 9, negative 5i, and negative 7i is negative 12i. Again, same thing that we did before with radicals. Now, when we multiply, again, same thing. Here, you would just distribute. 3 times 2 is 6. 3 times negative 5i is negative 15i. It's the same thing as if we were doing that. Simplify this, 7i. Alright, so now 7i times 2 is 14i. 7i times negative I is a negative 7i squared. Because we add the exponents just like an x times x is I squared. Well, I squared is really negative 1. So that's really like negative 7 times negative 1, or 7. Positive 7. So it's 14i plus 7. So I squared equals negative 1. So it turns the term to the opposite sign. So 7i squared becomes positive 7 with no I. Now, if we're multiplying things like this, we got to do FOIL, we got to do the box, we got to do double distribution. I'm going to do double distribution and the box. If you do FOIL, that's fine. Negative 3 times 3 is negative 9. Negative 3 times 2i is negative 6i. Then 7i times 3, 21i. 7i times 2i is 14i squared. So, I'm just going to rewrite those. And 14i squared is really just minus 14. I squared makes the 14 negative, and we get rid of it because that's 14 times negative 1. And now we can add our like terms. Negative 9, negative 14 is negative 23. 6i, negative 6i, and 21i is positive 15i. Same thing here. I'm going to do the box on this. So 9 and 4i, and 4 and 4i. 4 times 9 is 36. 4 times 4i is 16i. 4i times 9 is 36i. And 4i times 4i is 16i squared. So these two can be added up. So 52i. Remember, 16i squared is really like 16 times negative 1, so it's negative 16. And the 36 gives me a positive 20. So it's the same thing we were doing with radicals, because square root of I is a radical. It's the same thing.